New room-temperature superconductor offers tantalizing possibilities. The breakthrough could one day transform technologies that use electric energy, but it comes from a team facing doubts after a retracted paper on superconductors. Scientists announced this week a tantalizing advance toward the dream of a material that could effortlessly convey electricity in everyday conditions. Such a breakthrough could transform almost any technology that uses electric energy, opening new possibilities for your phone, magnetically levitating trains and future fusion power plants. Usually, the flow of electricity encounters resistance as it moves through wires, almost like a form of friction, and some energy is lost as heat. A century ago, physicists discovered materials, now called superconductors, where the electrical resistance seemingly magically disappeared. But these materials only lost their resistance at unearthly, ultra-cold temperatures, which limited practical applications. For decades, scientists have sought superconductors that work at room temperatures. This week's announcement is the latest attempt in that effort, but it comes from a team that faces wide skepticism because a 2020 paper that described a promising but less practical superconducting material was retracted after other scientists questioned some of the data. The new superconductor consists of lutetium, a rare earth metal, and hydrogen with a little bit of nitrogen mixed in. It needs to be compressed to a pressure of 145,000 pounds per square inch before it gains its superconducting prowess. That is about 10 times the pressure that is exerted at the bottom of the ocean's deepest trenches. But it is also less than 1/100th of what the 2020 result required, which was akin to the crushing forces found several thousand miles deep within the Earth. That suggests that further investigations of the material could lead to a superconductor that works at ambient room temperatures and at the usual atmospheric pressure of 14.7 pounds per square inch. This is the start of the new type of material that is useful for practical applications. Ranga P. Dias, a professor of mechanical engineering and physics at the University of Rochester in New York, said to a room packed full of scientists on Tuesday at a meeting of the American Physical Society in Las Vegas. A fuller accounting of his team's findings was published on Wednesday in the Nature, the same journal that published then retracted the 2020 findings. The team at Rochester started with a small, thin foil of lutetium, a silvery white metal that is among the rarest of rare earth elements, and pressed it between two interlocking diamonds. A gas of 99% hydrogen and 1% nitrogen was then pumped into the tiny chamber and squeezed to high pressures. The sample was heated overnight at 150 degrees Fahrenheit, and after 24 hours, the pressure was released. About 1/3 of the time, the process produced the desired result. A small vibrant blue crystal. Doping nitrogen into lutetium hydride is not that easy, Dr. Dias said. In one of the University of Rochester laboratory rooms used by Dr. Dias's group, Hiran Yupson, a graduate student, demonstrated the surprising hue-changing property of the material during a reporter's visit last week. As screws tightened to ratchet up the pressure, the blue turned into a blushing tint. It is very pink, Dr. Dias said. With even higher pressures, he said, it goes to a bright red. Shining a laser through the crystals revealed how they vibrate and unlocked information about the structure. In another room, other members of Dr. Dias's team were making magnetic measurements on other crystals. As the temperatures dropped, the expected squiggles appeared in the data plotted on a computer screen, indicating a transition to a superconductor. This is a live measurement we are doing right now, Dr. Dias said. In the paper, the researchers reported that the pink crystals exhibited key properties of superconductors, like zero resistance, at temperatures up to 70 degrees Fahrenheit. I'm cautiously optimistic, said Timothy Strobel, a scientist at the Carnegie Institution for Science in Washington who was not involved in Dr. Dias's study. The data in the paper, it looks great. Editor's picks. Is everyone judging you at the gym? New tricks for old apps. Would $650,000 buy a house in San Diego? One couple tested their budget. Continue reading the main story. If this is real, it's a really important breakthrough, said Paul C.W. Chu, a professor of physics at the University of Houston who also was not involved with the research. However, the if part of that sentiment swirls around Dr. Dias, who has been dogged by doubts and criticism, and even accusations by a few scientists that he has fabricated some of his data. The results of the 2020 Nature paper have yet to be reproduced by other research groups, and critics say that Dr. Dias has been slow to let others examine his data or perform independent analyses of his superconductors. The editors of Nature retracted the earlier paper last year over the objections of Dias and the other authors. "I've lost some trust in what's coming from that group," said James Hamlin, a professor of physics at the University of Florida. Nonetheless, the new paper made it through the peer review process at the same journal. Having a paper retracted does not automatically disqualify an author from submitting new manuscripts, a spokeswoman for Nature said. All submitted manuscripts are considered independently on the basis of the quality and timeliness of their science. At the conference on Tuesday in Las Vegas, so many physicists crowded a narrow meeting room that a moderator asked some to leave so that they wouldn't have to cancel the presentation. Once the room thinned out, Dias was able to present his findings with no interruptions. As he thanked the crowd, the moderator expressed regret that they had run out of time for questions. Strobel acknowledged the continuing controversy around Dias and the earlier extraordinary claims that have yet to be reproduced. "I don't want to read into it too much, but there could be a pattern of behavior here," Strobel said. "He really could be the best high-pressure physicist in the world, poised to win the Nobel Prize. Or there's something else going on." Superconductivity was discovered by Heike Kamerlingh-Ons, a Dutch physicist, and his team in 1911. Not only do superconductors carry electricity with essentially zero electrical resistance, but they also possess the strange ability known as the Meissner effect that ensures zero magnetic field inside the material. The first known superconductors required temperatures only a few degrees above absolute zero, or minus 459.67 degrees Fahrenheit. In the 1980s, physicists discovered so-called high-temperature superconductors, but even those became superconducting in conditions far more frigid than those encountered in everyday use. The standard theory explaining superconductivity predicts that hydrogen should be a superconductor at higher temperatures if it could be squeezed hard enough. But even the most resilient of diamonds break before reaching pressures of that magnitude. Scientists started looking at hydrogen mixed with one other element, surmising that the chemical bonds might help compress the hydrogen atoms. In 2015, Michael Erametz, a physicist at the Max Planck Institute for Chemistry in Mainz, Germany, reported that hydrogen sulfide, a molecule consisting of two hydrogen atoms and one sulfur atom, turned superconducting at minus 94 degrees Fahrenheit when squeezed to about 22 million pounds per square inch. That was a record high temperature for a superconductor at the time. Erametz and other scientists subsequently discovered that lanthanum hydride, a compound containing hydrogen and lanthanum, reached a superconducting temperature of minus 10 degrees Fahrenheit at ultra-high pressures. In the research described in the retracted 2020 paper, Dias's group used hydrogen, sulfur and carbon. With three elements, the scientists said, they were able to adjust the electronic properties of the compound to achieve a higher superconducting temperature. Not everyone believed that, however. Dias's main antagonist is Jorge Hirsch, a theoretical physicist at the University of California, San Diego. He focused on the measurements that Dias's group had made of the response of the carbon-sulfur-hydrogen compound to oscillating magnetic fields, evidence of the Meissner effect. The plot in the paper seemed too neat, and the scientists did not explain how they had subtracted out background effects in the plot. When Dias released the underlying raw data, Hirsch said, his analysis indicated that it had been generated by a mathematical formula and could not be actually measured in an experiment. From a measurement, you do not get analytic formulas, Hirsch said. You get numbers with noise. His complaints about Dias grew so persistent and strident that others in the field circulated a letter complaining about decades of disruptive behavior by Hirsch. Hirsch is a bull in a china shop contrarian taking aim at BCS theory, which was devised in 1957 by three physicists, John Bardeen, Leon N. Cooper and J. Robert Schrieffer, to explain how superconductivity works. BCS, he says, may in many ways be fundamentally flawed and able to explain the Meissner effect. He has come up with his own alternative explanation. Notably, Hirsch has been saying that there cannot be superconductivity in any of these high-pressure materials because hydrogen cannot be a superconductor. He has gained few allies. While Hirsch is careful to say that scientists other than Dias are not committing misconduct, he says they are deluding themselves.